So this is where we left last time, and we're still discussing the electric field. So on the figure on the left side, there's a non-conducting sheet, so it's like an insulator, and you can see that it's positively charged. And what we're doing is we are putting a positive test charge. That red positive charge is the positive red test charge. We are putting that on near the conducting sheet, and what we realize is it is being pushed away by that sheet. And so the reason is, again, there is an electric field created by the non-conducting sheet on that positive test charge, on the point where the positive test charge is, and that creates the force on the charge. So if you take some notes here, electric field lines extend away from the positive charge. That's where they originate. So the electric field lines originate from the positive charges, okay? And toward the negative charge. We don't have a negative charge here, so the electric field lines are going to go to the infinity in this case. But if you had a negative charge, then it would end up in the negative charge, and that's where they terminate. And in class we will show this with the FET simulation, and we will nicely see the electric field lines. So far hopefully it's clear that we explained how test charges are used to measure the electric field at any point. Again, that was not a physical charge, it was just we put it in, and now we check the force on it, and then there's force because there's an electric field. So we understand that so far that the electric field is created by the the force is created by the electric field. So here's the question: between the red and blue charge, which of them experiences the greater electric field due to the green charge? Okay, so green charges are, let's say, 1 coulomb. Okay, the units are not given here. It's positive 1 coulomb, the green ones are. And on the first case, we are putting a blue one, which is positive 2 coulomb, and the red one is positive 1 coulomb. And in both cases, the separation is the same. So I just want you to kind of think about Coulomb's law first. F12 is equal to Q1, Q2, R12 square, right? And again, we can just call it this is 1, this is 2, and we can do the same thing on the other case. And if you visually kind of see the equations, I think it's really easy to answer this question. And so we are looking for the electric field. So another important thing is to read the question very carefully. So the forces, if they were asking us to find forces, as you can see, when you multiply the charges, the first case will be 1 times 2 and the other one is 1 times 1. So and everything else is the same. So the first case would have double the force, right? But in this case, we are finding out the electric field. So they are trying to trick us. And again, reading the problem very carefully, and then think about what you are trying to find before doing it is very important. And it's gonna be, you're gonna see it. You're gonna make those mistakes coming up, because there are gonna be 4 different concepts that you can easily mix up and then find something else instead of the one that they're asking. So they are tricking us because they are telling us that there's like a charge on the point of interest where we are trying to find the electric field due to the green one. So really, just don't worry about the charge here, okay? This is just a point and this is just a point. at those points, at the same distance from the green charge, the electric field should be the same, right? It's the same distance, same charge. So the green charge is creating the electric field at a distance d, and it doesn't matter what charge you put in that point. So remember that you don't need another charge at the point to have an electric field. Electric field is due to green charge. It doesn't care if there is anything else. Force does care because it's an interaction. Okay, so in order to calculate this, use this equation and calculate the force, you have to have an interaction. You have to have two charges interacting each other. But electric field, you just need a source. That's it, and you can find the electric field and anywhere around it. So the answer should be there, the same for both. Now we're going to look into the electric field lines. So there are two cases we can compare, and one of them you can see that the direction is outward. So in the middle, the center one is our charge, and those lines and arrows are the electric field lines. And here we have negative 2q, it's given, and the direction of electric field is inward. So there are a couple things that we understand from this, first of all. So the electric field, let's just take some notes. E field points away from the positive charge, and it points toward the negative charge. Okay, so that makes sense then, because it was a negative charge, negative 2q on the right side, and the electric field lines are inward, radially inward. It's towards that negative charge. And this, what do you think about the part A, the sign of the charges? Since it's radially outward or pointing away from it, this should be positive charge, right? So by looking at the electric field lines, you can tell a few things, and right now we are focusing on electric field lines and the charge sign and the magnitude. Okay, so another thing that I think you realize is that the spacing, right? The first one we have, let's count, 8 of them, and the second one, I think we have 16 of them. So there are 8 lines here and 16 lines here. So the lines are doubled. So why did they double? So when we draw those two cases, we are doing it relative to each other. Okay, not every problem will be relative to each other, but the same problem, you will have the field lines relative to each other. And one of them has 8, the other one has 16 lines. So the part B is closely packed, and part A is separated. What do you think that tells you, right? So it's very straightforward. If they're closely packed, that shows the strength of the electric field. It doesn't mean that, let's say right here at the between the lines, there's no electric field. We don't show all of them. It is everywhere. Okay, so if I draw it here, I would draw it this way toward that charge. So there is an electric field in between spaces as well. But to make it easy for us, and then kind of like if you're picking 8 lines for Q, you have 16 lines for 2Q. Okay, so since the lines are 16 here and there's 8, this should be a magnitude of charge Q, and 2Q will produce double the strength of the field lines.